Hello folks. Well, this video is a carry-on from the previous one, so part 2 if you like, that covers magnetism and electromagnetism, the basics. And the reason that I'm doing these two videos is to go over what is magnetism and what is electromagnetism in response to the misunderstanding that the flat earth people have with regards to those two concepts. Okay, so let's see what we need to have this going. I'll just go over some of the stuff that we did before just to make sure that it's understood. Okay, alright, first of all, up here we've got a bar magnet moving through a coil. So the bar magnet moves through a coil, and as a result of moving through a coil, it creates electricity, creates a current. So what do you need for a current to be created? A, you need the magnet, so it can be whatever shaped magnet that's necessary. You need the coil, and you also need the movement. Okay, and there's actually a predictable equation for this over here. F equals NILB. So F is the force, okay, is equal to, so this will be the magnet, this will be the field force, will be equal to the number of turns, how many turns there are in the coil, okay, times the current, times the length of this coil, the length of the wire that's in this coil, okay, times the magnetic field strength, times the angle at which this goes through. So if it goes through at an angle, then as this turns through a magnetic field at an angle, okay, that angle determines the strength of that magnetic field. Okay. Now there's another thing called magnetic flux, where the force is proportional to the magnetic flux over the area. Okay. I'm not going to cover flux in this particular demonstration. However, if you have a look at it over here, now we have a transformer. Okay, I'll just explain that in a minute. Now, two things can happen. If you want to create a magnet, then again you can wrap a coil around a normal non-magnetic bar of, say, steel or iron. Okay, so if this was metal, an iron bar, and I wrapped a coil around it, well, just like this, around it, okay, and put some electricity through this coil in here, this will become a magnet. Okay, and the greater the amount of current that I put through this coil, the more magnetic, the stronger the magnetic field that this will have. Okay, now just taking from that, go back to the transformer. The transformer is really basically, if you think of it like this, actually, it's not a coil. Just think of this as a piece of metal, steel. It just goes around like this. So a hoop, a steel hoop. Now, on one side of the hoop, we put a coil of wire. So if you look at like that, over there, you can see that on one side we put a coil of wire. So let's say, for instance, I've got a coil of wire, 100 turns on one side, okay, and 10 turns on the other side, and on one side I've got 240 volts going into this particular wire. If I measure the voltage from this one, I'll only have 24 volts. Okay, that's how a transformer works. It works by what's called induction. Okay, so again, 100 100 turns of the coil on this side, put in 240 volts, 10 turns on that side, and I ended up with only 24 volts. That's a step down transformer. It works the other way too, by the way. If I put 24 volts in this side, I can get 240 volts out of this side. Okay, that's magnetic induction. Now, over here, I've got, if you like, the makings of a generator. Okay, so last time I spoke to you about how a generator works. We've got a magnet either side of a coil. So there's a coil. Either side of this coil, we have a magnet. So we'll have the magnet, this part of the magnet, north will be facing one side of it, south will be facing the other side. So we've got two magnets. This magnet on one side, that magnet on the other side. Okay, now, that then will create a magnetic field between those two magnets. Now, I've got a coil, and I put that coil in between those two magnets, so inside that magnetic field. Now, in order to generate electricity, I need to move it. Remember this, movement is critical. So, have a look at this graph over here. Might help you to understand it. This is a sine wave. Okay, and typically alternating current would have a sine wave graph like this. All right, the sine wave goes up, maximum voltage at 90 degrees, zero voltage at 180, minus maximum voltage at 270, and zero again at 360, and it just keeps repeating like that. That's why we call it alternating current. Okay, so what happens in this case over here? This coil turns through the magnetic field. And as it turns through the magnetic field, electricity is created. Okay, so let's have a look at how that compares with the graph. When the coil is parallel with the field, in other words, the field runs across the face of the coil, there is no voltage. Nothing will happen. And nothing will happen if it doesn't move. Now, as you turn the coil around, as you turn it around and you get to 90 degrees, that's the maximum voltage. Have a look at the graph. Started off at 0, gets to 90 degrees, that's the maximum voltage. Now, as you keep going, the angle's changing and then gets back to across the face of the field. In other words, parallel with the field. If it's parallel with the field, there'll be no electricity. Again, you can see that we've come back to 180 degrees. Voltage is 0. We keep going, and again, it's getting more and more and more, and eventually we end up with the maximum again, and again we go around and we end up back again with 0. And just this keeps going on and on and on. Okay, that's how it works. What's the critical thing here? Movement. It doesn't happen without movement. Okay, that's critical to this. So in other words, if you want to create electricity, you have to have movement. That's why you need the wind. That's why you need the steam. That's why you need gravity and all the other different methods of creating movement. Okay, movement costs energy. That's why you have to pay for electricity. You have to pay to make the steam. The steam turns the turbine, which turns this around. you've got to pay to make the steam. So therefore you've got to pay for the electricity. There is no free electricity around for you to get. Okay? So maybe you could harness the electricity that comes from the lightning, or some static electricity from high up, if you found a way to harness that, and then you'd have to store it in some sort of battery. But it's so there's so much electricity in such a small space of time that it's practically impossible to harness like that. Okay, so there isn't sort of loads of free electricity that you think there are that you could just go and get. So people like Marilyn and the like, who are proselytizing on the street, are telling people Tesla said there's all this free electricity that we can go and get. Really. If there was a way to get free electricity, they'd have it by now, like that. The closest thing you can get to free electricity is solar power. Okay, so I can explain that, how that happens later, but it's unrelated to magnetism, unrelated to electromagnetism. It's actually is related to photons, though. Okay, so that we can deal with in another video. How solar cells work. Okay. Which, by the way, is problematic for the flat Earth view of what the sun is, being close. Okay, that's problematic. I'd like to see how a flat earther describes how solar energy works. Maybe they will just deny that solar energy exists. Maybe people just put those flat things on their roof because they like the look of them. Well, no. The energy comes from the sun. Particular type of energy comes from the sun. Particular type of photons hit those panels, and that creates the electricity. Okay, it's not magic. Okay, we'll deal with that in another video. Anyway, so let's have a look at this. We've got two magnets over here, which is another thing. We're talking about pull and push. So there's flat earther, well, he doesn't like to call himself a flat earther. In fact, he denies that he even has any kind of model, but he is convinced that there's no such thing as pull force, that everything is push. Okay, that's the angry guy in the shed. He's done a video on me before, so I don't mind saying what he says. Okay, now, so basically there is a pulling force between magnets when the poles are opposed to each other. And the reason that happens is because when there is a magnetic field between an actual magnet, and it could be a magnet that's an electromagnet, like this, for instance, with electricity running through it, like a doorbell, for instance, like a microphone, for instance, like a speaker, for instance, where there's actually where we've got an electromagnet created. Okay. Then we've got some material that can be magnetized but isn't magnetized, for instance, some steel. Then, as you bring that into the magnetic field, the very, very surface of it, okay, the surface of the other one, the non-magnetic one, the crystalline structures start to line up. Okay, so the very face of it, electrons and the like, on the very face of it, start lining up, because they induced to line up by this magnetic field. Okay, so they start lining up, and this then starts pulling this towards it. So this will be north, south, north. This will now become north, and that will become south, and it will actually draw this magnet. The magnet will draw that material towards it. But that can only happen if this material is susceptible to being magnetized. And if you remember from the last video, the way that it is susceptible to being magnetized is that the crystalline lattices, the crystalline structures, are able to be aligned. If you can't align those, you cannot make a magnet, and no amount of strength of a magnet will be able to pull in the other material. So I can't make a piece of plastic be drawn in by a magnet. Okay, I can only do that with something that can be a magnet, like steel, where I can influence the lattices. Okay, what have we got here? We have the Earth. So this is the Earth. You can visualize that the Earth has a magnet through the center of it like this, and the magnetic field of the Earth goes around from the North Pole into the South Pole. And you'll notice, as I said in my last video, I'll repeat it, that the magnetic north is actually at our geographic, it's actually at our geographic south. Okay, so and the magnetic south is actually at our geographic north. Okay, all right. The field then goes from out of the north and into the south. Okay. Now we know this not because we're guessing. We know this because we have instruments that can actually measure this. Okay, we have instruments that can measure magnetic fields. Okay, now this is just an indication of how the Earth's magnetic field happens. There's the Earth, and we have inside the through, if you look at the cross section through that, we have an outer core. So between the crust and the outer core, we have we've got silicates. For instance, we have aluminium oxides, ferric oxides, aluminium silicates, ferric silicates, and a whole host of other silicates and oxides that are molten, semi-molten inside this outer core and beneath the crust. How do we know this? We have volcanoes. Okay, this stuff spews out of the volcano. We can see what it is. Okay, how do we know about this? This inner core. Again, those volcanoes create earthquakes. Shifting tectonic plates creates earthquakes. These earthquakes create P and S waves. By analyzing these waves, we can actually see what the center of the Earth looks like. So what the solid core that's right in the center of it, which is iron, and then we can see progressively what's around it. We can tell that from analyzing the seismic waves, the S and P waves. Okay, so we don't need to drill. That's unnecessary. So to say, the Flat Earth says we've only drilled 8 miles, so therefore we can't know what's in the center of the Earth, is just absolute nonsense. All that's doing is displaying your ignorance, okay, about where we've come so far with respect to geophysics. Okay, now, so let's have a look at the Flat Earth hypothesis that magnetism or electromagnetism replaces gravity. Well, first of all, within the model that Flat Earthers generally tend to speak about, they say that Earth is motionless. Well, this requires motion for it to happen. The Earth moves, and as a result of the Earth moving, spinning, it creates little eddies, and the Coriolis effect that happens within that inner core, between that inner core and the center core. Okay, between those, actually it's the outer core and the inner core. The inner core being the center one, the solid one. Between those is created these little eddies. The Coriolis effect from the movement of the Earth, from the spinning of the Earth, creates that, and it's this movement that creates electricity. It creates the electric field, and it's the electric field, as I've explained up here, that creates magnetism, that creates the Earth's magnetic field. Okay, right. Enough of the Earth is actually able to be magnetized. That's why it's possible to create a magnetic field. In parts of Western Australia, you can't even use a compass because the entire surface of the ground is made out of hematite, and hematite is Fe3O4, which is magnetite. So it's made out of hematite and magnetite. So magnetite is, as the word describes, it's actually magnetic, naturally magnetic. You can just pick it up and it will act like a magnet. Okay, this is iron oxide. Okay, now, no motion then. So if your model has no motion, it's not going to be an electromagnet. So that rubs that one out. However, if you agree that there is a motion, then we could look further at it. Okay, so there's no motion, so therefore no electric field. So therefore no magnetic field. So, no magnetic field, a compass wouldn't work. Okay, why would it? Okay, and it certainly wouldn't work consistently the way we have a compass now. Perhaps there'd be local places where, for instance, where there are magnets, magnetic rocks, for instance, like magnetite, and then they would point to those things. Okay, but you couldn't rely on it for something that you could navigate with. Okay, you can't rely on it and say it'll always point in one direction. It'll be pointing very higgledy-piggledy. That's why you can't use this in Western Australia, okay, in those parts of Western Australia. Okay, all right, so as a result of that, well, let's go for another one that I haven't written down. Again, most materials are not magnetic, so therefore this wouldn't apply to them. Electromagnetism wouldn't apply to them. Okay, so again, it cannot be a substitute for gravity. It's as simple as that. Okay, what have I got down here? All right, the other thing that's missing from the flat earth, I've written it down here, is think about what was required to make the magnetic field up there. Okay, it needed the ingredients of movement, and it needed the ingredients of electricity. So even if you argue that there's electricity, in static electricity, let's say when there's clouds and other particles around, okay, let's say there's that, then what about this electricity that you needed? How much of this electrical energy would you need to create such a massive amount of magnetic field? And why would it be so reasonably uniform that it is? It's not entirely uniform because there are, as I said, patches of different materials. However, for mostly it is fairly uniform. Why would it be uniform? And how much electrical energy would you need all the time? Okay, I think that pretty much covers it. So again, think about your model, the flat Earth model, and think about how rethink about this idea that electromagnetism would replace gravity. So clearly you can see, based on how electromagnetism comes to be and how it works, that that doesn't fit this hypothesis. Okay, so even if you believe the Earth is flat, the gravity, things that drop, cannot be explained by electromagnetism. Okay. All right. I think that's probably enough for magnetism. We'll see what we'll do next. I might have a look at photons or something like that, or I'll just wade through some of the other conspiracy things to do with flat Earth and see if we can't knock them on the head a bit at a time. Okay. So this isn't really videos about debunking as such. Okay, I just want to explain how the things actually work, to get rid of the misconceptions, and then you can make up your own mind about how that fits with your hypothesis that the Earth is flat. Okay, and bit by bit you'll notice that nothing actually fits in the flat Earth hypothesis, and yet everything fits the spherical Earth hypothesis. Okay, so if you like my videos, please press the like button. I notice lots of people watch it, but I don't seem to react much to it. Ask any questions you like. Okay, I'm happy to answer questions. My time on this is free for you. Happy to answer any questions that you might have with respect to any topic in physics. Okay, if I can't answer them, I'll steer you in the right direction and maybe get an answer for you at another stage. So ask any questions in the comments area. Okay. If there's enough of them, I'll probably do a video on it, and then we can have a look at it in a bit more detail, especially if it relates to flat Earth hypothesis. Okay. All right, and press the subscribe button if you haven't already. I'd appreciate that. Thank you. Have a good night.